So that means that we're going to draw structures that actually have the same basic skeletal structure, apparently. Okay. All right. But maybe where the double bonds or triple bonds are placed, in some cases triple bonds, they're placed in different places. Okay, because you can think about if you're surrounded by some different atoms, you could maybe steal a lone pair from one atom and use it as a double bond, or steal it from another atom that's bonded there that has a lone pair available and do a double bond there. Okay, so for example, all right, we have a resonance, 3 resonance structures, okay, drawn there for the nitrate ion. Okay, so when you draw nitrate, what will end up happening is you run out of electrons, but you still need to make nitrogen happy, so it has 8 electrons around it, right? Well, you could take a lone pair off of the oxygen right there, or to make a double bond, or that one, or that oxygen to make a double bond there, okay? Those are resonance structures, right? Because we're trying to represent kind of the reality of the molecule in real space, okay? But we can't really draw that. But something I do want to bring up here is, okay, like bond type, right? In terms of, single, double, or triple bonds, right? And relative bond length. What is the longest and which one's the shortest? Shortest. Okay, and single is the longest. Okay, because the reality is, if we were to measure the bond length between nitrogen and oxygen there, what is going on in real life is that it's actually a bond and a third. Okay, that's what's going on there. It's really a bond and a third, because we don't just have a single bond or double bonds present. It's kind of a blend. Okay, that last pair of electrons is really being shared between all of those bonds there. Okay, so if you flip to the next page, we keep on rolling. There's a way that we can draw that to kind of represent that. So we're trying to draw resonance structures to represent kind of real life here a little bit. So that's why we use this one. Okay. And because what we're trying to show you here is, look, here's ozone. That's one valid resonance structure on the left. Okay. Then we have another valid resonance structure for ozone on the right. But the reality is that it's really more of a blend of those two resonance structures. So that's why we have like the blue and yellow make green here. Okay. That last pair of electrons is really being shared between all 3 of those atoms in real life. Okay, because there's no bond difference in length between either oxygen. They're all the same difference. Okay, it's about a bond and a half. All right, it's between a single and a double bond. Okay, so that's kind of why we're doing that. All right, so and that's why we labeled this like a blue and yellow make green. Right, it's a blend between the different resonance structures that we're drawing. Okay, especially when the resonance structures are all equivalent to one another. Okay, they're all the same. Right now, there are resonance structures that we draw that are not equivalent. All right, where things are slightly different from one resonance structure to the next. Okay, and we'll get to that in just a second. Let's practice drawing a couple resonance structures. So I'll do the first one here, and then I'll have you guys do carbonate. Okay, so nitrite, NO2 minus. Nitrogen has 5 valence electrons. All right, we got 2 times oxygen. Right, each oxygen has 6. That's 12. We have a -1, right? -1 charge there, so we got to add an extra one and an extra electron in there. So we got 12, 18 electrons to dish out. So I'm going to put nitrogen in the middle. It is the least electronegative. Surrounded with oxygen, -4. We got 14 electrons left over. And I want to make our oxygens happy. So each one of those needs 6 more. 6, 2, 4, 5, 6. So we just use 12 electrons. Okay. 4 left over. When we have extra electrons and the outside atoms are happy, what do we do with our extra? Put them on the middle. Okay, yep, put them on the inside. 1, 2, 1, 2. We have 0 left now. All right. Now, both oxygens are good. They have 8, but our nitrogen only has 6. Right, so what are we doing? Yeah, we got to do some double bonds, right? So we're going to take some electrons. I'm going to take this first set of electrons from oxygen over there on the left, and I'm going to draw a double bond in. And there we go, that's good. Now, you can see here where I could just as easily have taken the electrons from the oxygen on the right, and drawn that, and we want to draw that as well, okay? That's just as easily an option there. So we're going to draw that one. And there we go. Oop, I almost forgot. There we go. So those are our 2 valid resonance structures. Yes, sir. Because it's see how it's NO2 minus? That's why we got it in there. Yeah, so I put it on both of them. Yeah, you would put it in brackets. It would just be like, if it was just this structure, all you need to do is just draw that one. You got to put in brackets and a charge outside of it. Yeah, if it's got a charge, you make sure you put that on there. Okay. All right, why don't you guys draw the carbonate one? We're in a gold medal. It's funny.
Oh, I didn't see that.
All 3. Yep. I draw them all. Draw them all. Yeah, so hopefully you guys came up with something like this. Why did it? Yes. Sometimes they'll be drawn for you already. And we might, like for the next part, is what a lot of times they'll be drawn for you already. We'll ask you like which one's the best. So, all right, so there you go. We okay with that? What if you drew them like I saw some people draw like where the carbon was here and you did it like this? See what I mean? Like where you drew it like that. That's okay too. You don't have to have it like drawn at the angles like I drew it. All right? You know what I mean? It'd be nice. You might get there once we start doing like the Vesper shapes and stuff like that, but this is fine. Okay? Any questions about that? Isabel? You good? All right. All right. All set? Okay. All right. So next page here. All right. So those are all equivalent Lewis dot structures, right? Because it didn't matter which way we put the double bond. It was all the same, right? It was all coming from really the same place. These ones are non-equivalent, which means they're not the same Lewis dot structures, okay, for the same molecule. So what we need to do is we got to draw them all, and then we're going to want to try and figure out how we know which one's the best. The way we're going to do that is we're going to use a thing called formal charge. And my favorite formula for formal charge is right here. Group number minus dots minus lines, okay, like that. And then we have a couple guidelines on the bottom there for formal charge too, which will help us pick which resin structure is the best. All right, so just in the effort of time here, I'm going to draw the sulfate ion, so 42 minus out here for us. So each sulfur has 6 valence electrons. We got 4 times oxygen, which is 24 valence electrons. We have that -2 in there, right? So we got to add 2 more electrons to our total. We got a total of 32 electrons. So I'm going to put sulfur in the middle, surround it with oxygens. Okay, so -8. Got 24 electrons left over. Well, that works out well because every oxygen needs 6. We have 4 times 6 is 24. So we'll use all of our remaining electrons here. So by 24, we have 0. Okay, that's valid resin structure. How can we draw another one here? Where's sulfur on the periodic table? 3rd row. So we could draw a double bond to sulfur. Okay, so we can do a double bond here to do an expanded octet for sulfur. There we go. All right, now there's one more that we can do, which is actually sulfur can handle one more double bond. All right, all these are valid resin structures. These all work. Everybody's got at least 8 electrons. Sulfur can have expanded octet, so it can handle all 12 of those electrons that it gets by doing those bonds there. All right, now we have to decide. Okay, well, which one's the best? Okay, which one's the best? Well, that's where we use formal charge to figure this out. Okay, we're going to take the group number that it is in, all right, minus the number of dots that are around it, minus the number of lines that are bonded to it. Okay, so for example, I'm going to do the formal charge for sulfur here. Red and green. And ooh, I zoomed in a lot. Okay, so for sulfur, it's got a group number of 6, right? Remember 6 for sulfur? Are there any dots around sulfur? Oh, -0. And how many lines do we got? 4. -4. We got a formal charge of +2. Okay, formal charge of +2 on sulfur. All right, each oxygen is going to be the same here, right? I And they're all the same, so we just do one here. So oxygen is also in group 6. All right. So 6 minus the number of dots around it. 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. Minus the number of lines. There's one line. So it's -1. So the formal charge for all the oxygens here is -1. So oxygen is in group 6 on the periodic table. Okay. We subtract out the number of dots around it, which is 2, 4, 6. All right, so it's 0. And we subtract the number of lines there. It's 1. So that's how we got -1. So it would be 6 minus 6 minus 1 to give us the -1. Okay. All right. Now, if we look at the next one here, and we do formal charge for sulfur here. So sulfur is group 6 minus the number of dots, which is 0, minus the number of lines. There are 1, 2, 3, 4, 5 lines. So it's got a formal charge of +1. Okay. And now we need to do this oxygen up top here. 6, right? Minus 4 from the dots, minus 2 from the lines, 0. Okay, and these oxygens are all the same as the other ones, right? Okay, so they're all -1 as well. -1, -1, -1. Okay, and we got to do the last structure too for formal charges. What's the formal charge on sulfur in this one? 0. Yeah, good. And the formal charge on those oxygens are -1. What's the formal charge on those oxygens that are double bonded? 0. Yeah, good. Okay, so now how do we choose which one's the best? All right, well, first thing we want to do, just to double check to make sure our formal charges are all right, the sum of the formal charges have to equal the ion's overall charge. Okay? So that means when we add up all the green numbers in here, they should all be 2-. Okay? Here we go. 2-, great. Those cancel. 2-. Awesome. Scroll there. 2 and 2. Okay. Oh, 2-. Awesome.
Just got
yeah.
So like, we can do that order. So I was like, can you like do anything for me? Like, we'll try it. And the guy's like, I don't know, I'm making 25 right now.
So I guess not.
I'm gonna call back to talk to his manager. That's just really funny because he's like, I don't make these decisions.
There you go. Yeah, stay in school. Stay in school. Stay in school. Pay $25 an hour at the Dunkin' D. All right. Now the last two, in order to pick which ones are right, okay, we double check their formal charges. They all work. The last two here, okay, all right, these last two help determine which structure is best. Okay, so what we want to see is each atom should have a formal charge as small or close to 0 as possible. So which one has the most zeros in it? The last one does. Okay, so that's probably a good sign that this is correct. Next thing we got to check is the molecule, a molecule or ion is most stable when any negative formal charges reside on the most electronegative element. Okay, so remember, most electronegative elements are close to fluorine, right? So our negative formal charges on this guy are on oxygen, Great. That's the most electronegative element there. So not only does it have the most zeros, but the negative parts, the negative formal charges are on our electronegative elements. Boom. That one's correct. That's the one that would be best in terms of the Lewis dot structures we drew. Yes? The second part is, okay, like for example, here, let me show you this one then, like, because this might help, like any negative formal charge should have the most electronegative element. Okay, so in this one, we got sulfur or oxygen, right? Oxygen's most electronegative. So we would want to see negative formal charges on oxygen, not on sulfur, right? So, for example, if we go down here, right, we'll do a couple of quick formal charges here. So carbon, it's number 4, it's in group 4, minus the lines, it's 0, right? Okay, so carbon 0 in that one. Carbon is 0 in each one, right? Because there's 4 lines connected to each carbon for each one of those. 0 and 0. All right, nitrogen is 5, right? So 5 minus 2 minus 3, 0. Okay. 5 minus 4, right? Minus 2, negative 1. Okay. All right, and then this one is 5 minus 6, that's minus 1, minus another 1, so that's negative 2. Okay, and all right, so sulfur over here is 6, right? Minus 6, minus a line, so that's minus 1. Sulfur over here, so we got 6 minus 4, minus 2 more is 0. And then this one here is 6 minus 2 is 4, minus another 3. That's going to be plus 1, right? Okay, so if I look at those, which one can we just get rid of right away? The third one, right? The third one, okay, this one's no good, obviously, right off the bat. So we got to compare these two. Okay, they've got zeros here, looking pretty good. Now we want to check to make sure our negative formal charge is on the most electronegative element. Okay, so between sulfur and nitrogen, who is the most electronegative? Who's closest to fluorine? Sulfur is. Yeah, sulfur's most is closest to fluorine. Right, whoever's closest to fluorine, right? So this is our best one. Because it's basically like, it's just like kitty corner. It's right next to it. Oh, yeah. Right, absolutely. Yeah. Yeah. Okay, so that's the one we want. Because it's most electronegative. There you go. Okay, we got the rest of the time to work on our online homework. Don't be careless on the online homework. A lot of multiple choice there. Write stuff out. Don't just guess. I'm going to start printing out the assignments for you because I think we'll do better that way.